This is 11-2, Pumpkin Ballistic Pendulum. An archer tests various arrowheads by shooting arrows at a pumpkin that's suspended from a tree branch by a rope as shown. When struck head on by the arrow, the pumpkin swings upward on the rope. The maximum angle theta that the rope makes with the vertical is different for each arrowhead that the archer tests. Each arrow, including the arrowhead, has the same mass m and is shot with the same velocity v0 towards the right. The arrowheads are made of different materials, however, and each behaves differently when it strikes the pumpkin, as described below. Embedded arrow strikes the pumpkin and remains embedded while the pumpkin swings to angle theta sub EMB for embedded. Pass arrow passes all the way through the pumpkin and continues traveling away from the archer while the pumpkin swings to angle theta sub pass. Finally, the bounce arrow bounces off the pumpkin backward towards the archer while the pumpkin swings to theta sub bounce. All right, you might have to take a second to think about what's going on there. For part A, we're going to rank the three angles from the greatest to the least. 1 for the greatest angle, 2 for the next greatest, and so on. If any two or all three of the angles use the same number for their ranking. And then B is going to explain why. Okay. So before we say the answer, this is a conservation of momentum question combined with a conservation of energy question. So it doesn't make a difference which angle you attack this from, but if we start with conservation of energy, right, we ask ourselves, and this is kind of what we're writing on our little note sheet, what will cause greatest theta, right? Because that's part A. And remember, our theta is from the vertical. So large theta equals large height, right? And so what are we doing here? We're converting kinetic energy into gravitational potential energy. So if we want a large height, we need a large what? We need a large 1/2 mv squared. So we need to argue that the pumpkin that's moving the fastest after this collision is the one that's going to go the highest. So you need to somehow justify that. And that's not difficult. That's just a conservation of energy argument, okay? Because that's where we're going with this. We've got to ask ourselves, in which case is the pumpkin going the fastest? And that's going to be conservation of momentum question. But once we figure out who's moving the fastest, then we figure out what's going to go the highest. And it turns out it's the faster arrow. So once you make this argument here, and you're going to get, I'll go over the rubric in a moment, but you'll get a point for the justification that the higher angle is the higher speed. Okay, so now we got to figure out which pumpkin is moving fastest. Okay, so at the beginning of this, when the arrow is fired and the pumpkin is at rest, all of the momentum of our system is the mass of the arrow times the velocity of the arrow. That's our before situation. Our after situation, the total momentum is the mass of the arrow and the final velocity of the arrow plus the mass of the pumpkin plus the final velocity of the pumpkin. So we've got to take that all into account. But if we think of this as a conservation of momentum question kind of as a system, what we have is momentum lost by the arrow equals momentum gained by the pumpkin, right? Whether or not the arrow is embedded in the pumpkin or not, it doesn't matter, okay? Momentum is going to be lost by the arrow and it's going to be gained by the pumpkin. So in which situation does the arrow lose the most momentum? Now remember, momentum's a vector quantity, so we're looking for the greatest change in velocity of the arrow, not the greatest change in speed, but the greatest change in velocity. And the greatest change in velocity is going to come when it starts out in this direction and ends up in this direction. So this is the greatest, right? It's not the greatest change in speed because we don't know how much it's going to slow down. We don't know how much the pumpkin weighs, any of that. But this, any way you slice it, this is a greater V than this is fast, this is slow, right? This is the pass situation and the embed situation. This delta V is going to be less. So our theta bounce is going to be number 1. Okay, now we have to decide between theta embed and theta pass. And the question again is, where does the change in momentum of the arrow is equal to change in momentum of the pumpkin. Now, if we want a higher change in momentum of the pumpkin, we need a higher change in velocity of the arrow. So, which situation results in a greater change of speed for the arrow? Well, it's the embedding, okay? Because in the embed situation, the pumpkin and the arrow have the same speed after the collision. In the pass situation, the arrow is going to be going faster than the pumpkin once it goes through. So 1 is bounce, 2 is embed, and 3 is pass, right? So you've got to bring a lot to the table here. You got to have your conservation of energy question or argument that justifies the fastest pumpkin is going to give the highest speed, but then the rest of it is a conservation of momentum question. So there are 1, 2, 3, 4, 5, 6, 7 points for this paragraph. 1 point for using conservation of momentum. 1 point for saying that the momentum lost by the arrow is gained by the pumpkin. 1 point for explaining why the bounce transfers the most momentum. 1 point for explaining why the pass arrow ends up faster than the embedded arrow. 1 point for saying the arrow that slows down the most transfers the most momentum. 1 point for justifying that the angle is related to the speed. That's your conservation of energy point. And then 1 point for a logical paragraph. So these big 7-point paragraphs, I mean, you can make a good argument and maybe get 5 to 7 of those, but that's where all 7 of those are from. And that idea, for me, the most important part of that problem is the bouncing part. Realizing that the bouncing is the biggest change in velocity. Because we get confused when we're talking about conservation of momentum, conservation of energy, and energy doesn't have a sign, right? We just add it all up. But sometimes we forget that momentum does have a sign, and something bouncing off of something creates a very large change in momentum. So that's the second one from assignment 11.